Okay. So up to last class, we have completed natural magnetism. The next chapter is electromagnetic induction and AC. It's basically unit number fourth. First was electrostat, second was current, third was magnetics and magnetism. This is unit number fourth. It consists of two chapters, EMI and AC. So the weightage of these two chapters collectively was 8 marks. But now since this year syllabus is reduced, so maybe it gets more weightage. It consists of two chapters. The one is EMI, electromagnetic induction. Electromagnetic induction. Second is alternating current, which is AC. One is EMI, second is AC. This EMI is basically chapter number 6 of NCERT, and this is chapter number 7. Let's start with electromagnetic induction. See the introduction of this chapter. So up to last chapters, we have studied that if you have a conductor and if you can pass current through this conductor, then this conductor with current will generate a magnetic field. This will generate a magnetic field. So if you have a conductor and you pass current through that conductor, then that due to that current, this will generate some magnetic field. But in this chapter, we will study the reverse process. We will basically study that if you have conductor plus magnetic field, then you can generate current. This is basically the principle of dynamo, AC dynamo. Dynamo that we usually call generator. What happens in a generator? In a generator, you have a conductor, you have magnetic field, you're moving your conductor, rotating your conductor in the magnetic field, and it generates current. So in this chapter, we will study this thing, that conductor plus magnetic field will give you current. Till now, we have discussed only one source of current, and that was cell. Up to chapter number 5, there was only one single source of current, and that was cell. But now we will talk about one more source of current, and that is changing. That is basically this thing. This will generate EMF. Most of the theories that we will do in this chapter were done by Faraday's. So this is the introduction of this chapter, that we'll see how to generate EMF or voltage without current, or how to generate current using just current and conductor and magnetic field. See, nature is very symmetrical. If nature allows that if you pass current through a conductor and you can generate some magnetic field, then reverse is also possible. That means if you have conductor and a magnetic field, then you can easily generate current. We start this electromagnetic induction with the concept of magnetic flux. The concept of magnetic flux match with that of electric flux. In electrostatics chapter number 1, we did electric flux. Electric flux was the number of electric field lines crossing an area normally. Just like electric flux, we have magnetic flux, which is basically number of magnetic field lines crossing area normally. So the number of magnetic field lines which are crossing an area normally is known as magnetic flux. This is magnetic flux. So it's number of magnetic field lines crossing an area normally is magnetic flux. So if you have a surface, let's say 4 magnetic field lines are crossing this surface, then your flux would be 4. Magnetic flux will be 4. But usually the number of magnetic field lines is not given. The thing which is given is area and the strength of magnetic field. So let's say you have this area. Okay, so can you tell me what is the direction of this area? Okay, the direction of area is outwards normal. The direction of area vector is outwards normal. Direction of area vector is outwards normal. This outwards normal is the direction of area vector. This is direction of area. So if you have an area like this in YZ plane, then the direction of this area is along x-axis. If you have an area in XY plane, then the direction of area is perpendicular to XY plane. So this is the direction of area vector outwards normal. Area is S, and this is the strength of magnetic field. The angle between the magnetic field and the area vector is theta. So you can write your area vector S as, this is your area vector, which is basically S into n cap. This is your area vector. So the definition of magnetic flux is, we represent it by phi b, that's magnetic flux, and the magnetic flux is magnetic field dot area vector. This is the definition of magnetic flux. If you open this dot product, then you will get bs cos theta. And always remember, this theta is the angle between, it is the angle between magnetic field, angle between magnetic field and area vector. When I say area vector, that means normal to area. Remember, if this is area vector, let's say this is magnetic field. If I give you this angle, let's say if I call that this angle is 30 degree, this is not theta, because this angle is not with the normal, this is with the plane. You will use this angle. You will use this angle, which is 60 degree. This will be your theta. So this angle is important. That angle that you take is always with respect to area vector, not with respect to the plane of area. So that is 3 theta basically. Now, just like electric flux is a scalar, just like electric flux is a scalar quantity, its SI unit is Tesla meter square. Magnetic field is Tesla, area is meter square, which is known as Weber. So the SI unit is Weber. If we talk about the CGS one, CGS unit is magnetic field is Gauss, area is centimeter square. So that's Gauss centimeter square, which is known as Maxwell. That's Gauss centimeter square. This is Gauss, CGS unit of magnetic field. If you calculate relation between Weber and Maxwell, so remember that 1 Weber is 10 raised to the power 8 Maxwell. This is the relation between Weber and Maxwell. 1 Weber is 10 raised to the power 8 Maxwell. Okay, there's one more concept here, that if your magnetic field is variable, remember, for variable magnetic field or for a curved surface, if you have a field which is variable or you have a surface which is curved, your magnetic flux phi b is integral of b dot ds. Although there is not even a single numerical in NCERT which use this concept of curved surface or variable field. But if you came across any magnetic field which is variable magnetic field, if you came across any magnetic field which is variable or a surface which is curved, then your magnetic flux is integral of D dot ds always. There's one more thing which is known as Gauss law in magnetism. Gauss law in magnetism says that if you have a closed surface, then magnetic flux through a closed surface is always zero. Is not always. If you have a closed surface, then magnetic flux through that closed surface is zero. We will discuss why it is zero. But if you want to calculate magnetic flux through a closed surface, then put a close sign over the integral. D dot ds will be equal to zero. This zero magnetic flux shows that magnetic monopoles does not exist. Only north pole and south pole exist. This shows that magnetic monopoles does not exist. See why this is zero and how you can relate this to this point. So you have a closed surface. Inside this closed surface, I put a magnet. So whenever you have a magnet, it's a dipole. It consists of north pole as well as south pole. In magnetism, you cannot have a monopole. It's not possible that you have just a north pole or a south pole. Whenever you have a magnet, it's combination of north pole as well as south pole. So what happens is magnetic field comes out of the north pole and enter in the south pole. So if I count flux, then magnetic fields coming out of the surface is positive flux. I'm repeating. Magnetic flux coming out of the surface is a positive flux. But magnetic field entering the surface is negative flux. So one magnetic field lines leave the surface, it's plus one. One magnetic field line enter the surface, it's minus one, which is zero. In the same way. Magnetic field line leave the surface, that's plus one. One magnetic field line enter the surface, that's minus one, so it's zero. Total flux is zero. So this is Gauss. The reason of Gauss law is the second point. That Gauss law in magnetism, total flux is zero. That means the outwards flux is equal to inwards flux. Means positive flux is equal to negative flux. Total flux is zero. Which basically shows that the source of magnetic field is always a dipole, a combination of north pole as well as south. Let's solve few numericals on this concept. So magnetic field so this is your area. This is the direction of area vector. This is your magnetic field, which is 2 Tesla. See, this angle is 30 degrees. Calculate magnetic flux. This is simply Bs cos theta. Yes, you're correct. So magnetic field is 2, area vector is 10 meters square. The angle between the magnetic field and area vector is 60 degrees. So this is cos 60. So your magnetic flux is 20 into cos 60 is half, it's cancelled out. So your magnetic flux comes out to be 10 Weber. So that's your magnetic flux. Okay, solve one more numerical. magnetic field B is equal to 10 I cap plus 3j cap plus k cap Tesla exists in space. Calculate flux through an area of 2 meters square in YZ plane. I'm giving a hint that direction of area is perpendicular to area. If your area is in YZ plane, then the direction is along x-axis. So you can write your area vector as twice of I cap. Your magnetic field is, no Johanna, you're not taking dot product properly. 3j cap plus k cap. It's 2 I cap meter square. This is Tesla. Your magnetic flux is just the dot product of magnetic field and area vector. So magnetic flux is just, it's 10 I cap, 3j cap plus k cap dot 2 I cap. There is no j and k components. You can write this as 0 j cap plus 0 k cap. So the magnetic flux is multiply the ith component with the ith component. So that's 20. No I cap. Multiply jth component with the jth component, which is 0. Kth component with the kth component, which is 0. So that comes out to be 20. So this is your magnetic flux, which is 20 Weber. After this magnetic flux, the next topic is Faraday's experiment. Okay, before starting background, this Faraday's experiment, just listen some background of these experiments. Through this experiment, Faraday was trying to discover a new source of EMF. Before these experiments, there was only one source of EMF, and that was cell. If you have a cell, you can generate EMF. But through these experiments, Faraday was trying to generate another source of EMF, another independent source of EMF. That basically leads to your generator. In all these experiments, the one thing is common, and that one thing is whenever magnetic flux change, whenever in any system a magnetic flux change, due to that change in magnetic flux, EMF will induce in that system. So in all experiments, the statement is common that changing magnetic flux will induce EMF. Basically, this statement changed the world. See, whatever the industries or factories you run on electricity, they basically run on AC current, not on DC current. And the source of AC current is generator. The basics of the starting point of generator is these experiments. You cannot run industries using cell or batteries. So after this law, Tesla makes generator, and after generator, the industrial revolution came. So even in history, this law keeps an importance. Anyway, so Faraday's experiment, whenever magnetic flux linked with a coil change, an EMF is induced. That's Faraday's experiment. So to prove this thing, Faraday did series of experiments. The first experiment is induced EMF means changing magnetic flux is generating EMF. Due to magnetic flux, and EMF is generating. That is basically induced. Usually, we don't, in physics, we prefer not to write this generate word because that will eventually mean that you are generating energy, which is not possible. Total energy is conserved. So instead of generating, we use word induce. That due to changing magnetic flux, an EMF is generated. That is mean by induced term. Let's take this coil. This is coil C. I have connected a galvanometer through this coil. There is no cell, no battery, nothing. So what you expect the deflection of the galvanometer? Galvanometer will have zero deflection, or it can have some non-zero deflection. I have not connected this coil with any cell or battery. It's just a coil and a galvanometer. What do you expect? The reading to be zero or non-zero? Yes, Resham is correct, Fatma is correct, Joanna and Johanna, yes. No deflection. Because there is no cell, no battery. Then Faraday placed a magnet near this coil. The magnet will definitely generate some magnetic field. So some magnetic field is passing through this coil. So the magnet is generating some magnetic fields, and these magnetic fields are passing through the coil. When magnetic field passes through the coil, some magnetic flux gets linked with the coil. See, magnetic field lines are passing through the coil, due to which some magnetic flux gets linked with the coil. If the magnet is stationary and the coil is stationary, then this magnetic flux is constant. But if this magnet starts moving towards the coil, then magnetic field will increase. See, if magnet comes closer to the coil, then the magnetic field due to the magnet will increase, because magnetic field decrease with the separation. And when magnetic field increase, flux increase, and due to increase in flux, you will Faraday experience noticed a deflection in the galvanometer. This galvanometer shows a deflection in one direction. This deflection shows that there is some current in the circuit. And the cause of that current is simply the motion of the magnet. The motion of the magnet changes magnetic field. And here, this is the formula of magnetic flux. So when magnet moves, magnetic field change, due to which flux change, and this changing flux generate or induces an EMF. That EMF is responsible for the deflection. Is it clear? This first experiment? First experiment of Faraday. Okay, what do you expect if this magnet comes to rest? He's moving the magnet and this galvanometer is showing some deflection. What if this magnet comes to rest? If magnet is at rest, what would be the deflection if this magnet comes to rest? Yes, what deflection are you expecting if this magnet comes to rest? Yes, Johanna, you are correct. Fatma, back to normal means zero, right? So if this magnet stops, that means no change in magnetic field, no change in flux, induced EMF will be zero. So the change of induced EMF will last till the flux changes. Once the flux becomes constant, induced EMF is zero. Then Faraday do one more experiment. He take the same coil. Even if he move this magnet away from the coil, then again, magnetic field will change, flux will change, coil will show deflection but in opposite direction. To induce EMF, flux should change. It can either increase or decrease. Even if flux increases, then there is some induced EMF. If flux decreases, then there is some induced EMF. But if flux remains constant, then induced EMF is zero. But if flux increase, then direction of current is different. If flux decrease, then direction of current is just opposite. How to calculate the direction of current? That we will do after this experiment. So this is the coil. This is the magnet. This is the magnetic field. Fatima, it's due to magnetic field. See, if I take a magnet, this is north pole and this is south pole. If I move away from the magnet, the strength of magnetic field will decrease. Na? If I take a magnet, as far as I go away from the magnet, the strength of magnetic field will decrease. If magnetic field here is 10 Tesla, 8 Tesla, 7 Tesla, it keep on decreasing. So if I am bringing this magnet closer to the coil, then what will happen to B, Fatima? If I am taking this magnet closer to the coil, what will happen to B? It will increase, decrease, or remain same? It will increase. So if B increase, then phi will increase, flux increases. If I take this magnet away from the coil, then B will decrease, magnetic field will decrease, and flux will decrease. In the third experiment, we take the coil. In fact, we take two coils. He connected one coil with a galvanometer and he take another coil and connected this coil with a key. So when he connected this coil with the key, this coil will generate some magnetic field. Whenever current passes through a coil, this coil will generate some magnetic field. Means the magnetic flux is linked. I call this as coil 1. I am calling this as coil 2. Some flux is linked with the coil 1. Okay, can you tell me if C1 and C2 are stationary, then flux is constant or variable? Throughout the chapter, you have to do just constant or variable flux. That's it. Yes, if both C1 and C2 are at rest, then flux is constant. No change in flux, no induced EMF. But if I start moving this C2 towards C1, then what will happen? If I start moving this C2 towards C1, then what will happen? Flux will increase, right? Flux will increase due to which an EMF, induced EMF, comes in C1. The C1 will have an induced EMF. Okay, let's take one more example. Last experiment. So he took two coils, one coil C1, he's connected this coil with a galvanometer, and he took another coil C2. He connected this coil with a cell and cell with a key, and this is it. This is coil C2. As he closed this key, as soon as he closed this key, when he just closed this key, then there is some deflection in the galvanometer. And after some fractions of second, let's say after some 1 second, this deflection comes to zero. I'm repeating again. He's not moving any of the coil. He just switched this key off, close this key. Close the key means open this, on the switch. Switch is on. He just closed this key. As soon as he closed this key, some current flows in coil C1, which can be detected by the deflection of this galvanometer. After some fractions of second, that current comes to be zero, means deflection of galvanometer is zero. So as soon as he switched this key, closed this key, there is a deflection in the galvanometer. After a few seconds, this deflection comes out to be zero. See, when you just close this key, the current in this coil starts increasing. Means if you take a wire and you take a cell, before closing the key, your current is zero. After closing the key, the current increases gradually. So when you switch this key, you close this key, the current in this coil starts increasing, starts from zero value to a maximum value. When the current increases, you know in Biot-Savart's law, your magnetic field is directly proportional to current. On switching this key closed, current in coil C2 increases, due to which the magnetic field of the coil C2 increases. This increasing magnetic field is linked with this coil C1, due to which flux of this coil C1 changes, and due to the change in flux, you will get an induced EMF. Are you getting it? What happened on just switching off the key, or on just closing this key? Current starts increasing, then magnetic, and if current is increasing, that means magnetic field is increasing. Flux increase, you will have some induced EMF, which can be detected by the galvanometer. But after some time, this current becomes constant. It increase from 0 to a maximum value, then it becomes constant. Once the current becomes constant, that means your magnetic field is constant, your flux is constant, deflection in the galvanometer is zero. That's why as soon as you switch this key close, the galvanometer shows deflection. After some time, the deflection becomes zero. Because the current becomes constant, magnetic field becomes constant, flux becomes constant, induced EMF is zero. So is it clear, this last experiment? This will do in more detail in mutual induction. That's basically the mutual induction. Sure. So in all these 4 experiments, what is common? The changing magnetic flux will induce EMF. Okay, just note these experiments. I'm not dictating anything. You will do these experiments from NCERT. On the second page of NCERT of chapter number 6, you will find these experiments. You can read these experiments from NCERT. I don't want to waste the entire lecture in just writing the details of this experiment. Okay, just note it down. Then we'll do Faraday's law. We'll start Faraday's law of electromagnetic induction. But at least make these diagrams.
Assignment.
Okay. The next is Faraday's law of electromagnetic induction. So the Faraday's law of electromagnetic induction says, on the basis of these experiments, Faraday give this law, Faraday's law of electromagnetic induction. This law says, whenever magnetic flux linked with a coil change, an EMF is induced in it, induced EMF is proportional to rate of change of flux. Induced EMF is proportional to a rate of change of flux. That is Faraday's law of electromagnetic induction. So if phi1 is flux at time instant t1, this is phi1. Phi2 is flux at time instant t2. And this is delta phi, which is phi2 minus phi1. change in flux. This is delta T, which is T2 minus T. So delta phi is change in flux in time delta T. So the change in flux in time delta T is delta phi. So induced EMF E. So the Faraday's law of electromagnetic induction says that induced EMF is proportional to delta phi over delta T. So if you remove the sign of proportionality, you will use a constant K. So it's K delta phi over delta T. So E is equal to K delta phi over delta T. In all system of unit, this K is basically equal to -1. So this induced EMF comes out to be minus of delta phi over delta T. Yes, that's induced EMF, right? It's minus of delta phi over delta T. So here this negative sign is itself a law. It's a law in itself, which is known as Lenz's law. We will discuss Lenz's law, but for the time being, you can understand that you can just see this negative sign basically represent Lenz's law, which is law of conservation of energy. If you remove negative sign from this equation, then energy conservation gets violated. We will see how this negative sign is controlling that energy conservation, but this negative sign basically shows conservation of energy. So that's basically Lenz's law, minus of delta phi over delta. If you want, you can write this mod of E as delta phi over delta T. Modulus of E is delta phi over delta T. That's Faraday's law of electromagnetic induction. So this E is minus of delta phi over delta T. This is the average EMF. This is the average EMF. For instantaneous EMF, the standard procedure, you can write that limit delta T tends to 0 minus of delta phi over delta T. Or you can write this as minus of d phi over dt. So this E comes out to be minus of d phi over dt. So this is instantaneous EMF, minus of d phi over dt. So if you're differentiating flux with respect to time, then this is instantaneous EMF minus of d phi over dt. You can also calculate current. If R is resistance, then you can easily calculate current. That current I is E by R minus 1 by R d phi over dt. That's your current. Basically, it's induced current. If you have induced current, you can calculate charge through the conductor. So you can write your I as dq over dt, which is minus 1 by R d phi over dt. So this dt will cancel this dt, and you are left with that charge is just minus of d phi over R. So that's average EMF, that's instantaneous EMF. This is instant induced current, and this is the expression of charge. So that was electromagnetic induction, Faraday's law of electromagnetic induction. One thing is important here, that if your circuit is open, in open circuit, induced EMF exists. Even if your circuit is open and you change flux through that circuit, then you will have induced EMF. But in open circuit induced current is 0. Because for current, you need a closed circuit. But in closed circuit, you will have both EMF as well as current. In closed circuit, both EMF and current. See, the first question is flux linked with a coil is, this is the flux linked with the coil, which is 3t square plus 2t plus 1. Calculate induced EMF first in 0 to 2 seconds, second at t equal to 2 seconds. So the part 1, EMF is minus of delta phi over delta t. So it's minus of, it's phi 2 minus phi 1 by T2 minus T1. So your T1 is 0. If I substitute all values here, then your phi 1 is 1 Weber. T2 is 2 seconds. If I substitute all values here, then this is 3 into 2 square plus 2 into 2 plus 1. So that's 12 or 416 or 117 Weber. If I substitute all values here, then this is minus of phi 2, which is 70, minus phi 1, which is 1. It's T2, which is 2 minus 0. So E is minus 16 by 2. E is minus of 8 volt. It's because if I substitute T equal to 0 in this equation, Fatma, I'm substituting T equal to 0 in this equation. Phi 1 is, it's 3 into 0 square plus 2 into 0 plus 1, it's 1. Right? And the phi 2 is 17. In the second part. Now, t equal to 2 seconds means it's instantaneous. For instantaneous, to differentiate your phi with respect to t, it's minus of d phi over dt. It's minus of d over dt of 3t squared plus 2t plus 1. So your E is minus of 6t plus 2. Put t equal to 2 here. If you put t equal to 2, then this is minus of 6 into 2 plus 2. So it's minus of 14 volt. So this is your initial flux. This is your final flux. This is the time taken between initial and final. So you can easily calculate EMF, and when you have this resistance, you can calculate charge. At a time, this flux passes through it. If flux falls to this value in 0.1 second, so that's your initial flux, this is your final flux, and this is the time taken from initial to final flux. Delta phi is N, which is 1000. Phi 2, which is final flux, 0.5 into 10 raised to the power minus 4. Minus phi 1, which is 5.5 into 10 raised to the power minus 4. So this delta phi comes out to be 1000. If I subtract them, then this is minus 5 into 10 raised to the power minus 4. Then your delta phi comes out to be minus 5 into 10 raised to the power minus 1. So you can write your delta phi as minus of 0.5. This is your change in flux. The time interval is 0.1 second. So you can easily calculate induced EMF. It's minus of delta phi over delta t. If I substitute these values, it's minus, then your delta phi is minus of 0.5, delta t is 0.1, it comes out to be 5 only. Your E comes out to be 5 volt. Is it clear? For charge, you can use this thing that your charge delta Q is just change in flux divided by R with a negative sign. So it's your change in flux is this minus 0.5. So it's minus of minus 0.5 divided by R. Your R is 10. So your charge comes out to be 0.05 coulomb. A coil of cross-sectional area A when coil rotates by first part 0 degree to 90 degree position, second part 0 degree to not 0 to 90, 90 to 180 degree position. First part we will solve together, second you will solve. So coil of cross-sectional area A lies in a uniform magnetic field with its plane perpendicular to the field. So if this is the coil, then this is the magnetic field. Magnetic field is perpendicular to the plane of coil. That means magnetic field is parallel to the plane of coil. So can you tell me how much is theta? The angle between magnetic field and area vector? If B is just perpendicular to area, it's parallel to n cap. How much is theta? Right, theta is 0 degree. So you can easily calculate flux that your initial flux is BA cos 0. So you can write that your initial flux is just BA. So the strength of magnetic field is B, area is A. Okay, that's good. Now this coil rotates by 180 degree. 180 degree, not 180, 90 degree. 90 degree means earlier the coil was like in this way. This is magnetic field and this is plane of the coil. Now this coil rotates by 90 degree. It rotates like this way. Earlier this is magnetic field and this is the plane of the coil. Now your coil rotates by 90 degree. So this is your magnetic field and this is the area vector of the coil. Now can you tell me how much is theta now if coil rotates by 90 degree? Can you tell me how much is theta now? 0. Yes, it's 90 degrees. See, this is your magnetic field. This is your magnetic field in this direction. Okay. Earlier, your coil was in this perpendicular to magnetic field, so that area vector is parallel to magnetic field, angle is 0 degree. But now your coil rotates by this 90 degree. It rotates by 90 degree in this way. Now the area vector is outwards, right? So this is your area vector and this is your magnetic field. They are perpendicular now. Right, Fatma? Angle would be 90, not 0. So when the coil rotates by 90 degree, so your theta comes out to be 90 degree now. Your final flux is BA cos 90. Cos 90 is 0, so your final flux is 0. Phi initial is B into A, phi final is 0. Okay, can you just tell me how much rotation is completed in if it rotates by 90 degree? This is the initial position of the coil. See, this is the initial position. It rotates by 90 degree, then by 90 degree, then 90 degree, and then 90 degree, one complete rotation. If it rotates by 90 degrees, this is half rotation, 1/4 rotation, 3/4 rotation, how much? It's 1/4 rotation, right? So if the rotation is 1/4, the time taken for one complete rotation means if coil starts from here and it come back to here, that's one rotation. Time taken for one complete rotation is T, for 1/4 rotation is T by 4. So if I calculate EMF, that EMF is minus of final flux minus initial flux by delta T. So when you substitute all these values, you will get this is minus BA4 by T. In the second part, your coil is rotated from 90 degree to 180 degree. So when your coil is rotated by 90 degree, that means your theta, this we discussed in the last part that your theta is 0 degree. Theta is 90 degree. If your coil is rotated by 90 degree, then your initial flux is, it's BA cos 90, its phi I comes out to be 0. When you rotate it by 180 degree means, see, this is your coil, this is initially your coil, and this is magnetic field. They are perpendicular, area vector is parallel. 180 degree means it goes like this. Now the area vector is here. This is your area vector. See, initially this is your area vector. When your coil rotates by 180 degree, that means it's like this. Your area vector is in this direction. So if your area vector is in this direction and your magnetic field is in this direction, they are opposite to each other. So you can say that your theta now is 180 degree. Your final flux is BA cos 180. Your 180 is minus 1. So your final flux is minus of BA. That's minus of BA. Now, if I substitute all values here, then your E is minus of delta phi over delta T. So it's minus of delta phi, which is phi final minus phi initial over delta T. So it comes out to be minus of minus BA, phi initial is 0 over delta T. Now this is completing the half rotation. It's completing, no, it's not completing the half. From 90 to 180, it completed another 1/4 rotation. Sorry, your time will be 1/4 again. So from 90 degree to 180 degree, it completed another, see, from 0 to 90 degree, 1/4 rotation, then 90 to 180, it's 1/4 rotation, then 180 to 270, another 1/4, then 270 to 360, another 1/4. So 90 to 180 means time is T by 4. So when I substitute all these values here, your induced EMF comes out to be, it's minus of your delta, it's BA over T by 4. It comes out to be 4 times BA by T. So all these questions were based on electromagnetic, Faraday's law of electromagnetic induction. The next type of questions that you will get will be based on Lenz law. So see what is Lenz law. Lenz law basically explain that negative sign in Faraday's law. It gives you the direction of current, that what is the direction of induced current in your circuit is given by Lenz law. This also tell you about the polarity of EMF. Where is the positive terminal of this potential? Where is the negative potential? That polarity of potential is also given by this Lenz law. So the Lenz law simply says that direction of induced current is such that it opposes its cause. it opposes its cause. That is change in flux. So the Lenz's law says the direction of induced current is such that it opposes its cause, that is change in flux. So basically, in a circuit, induced current try to oppose change of flux. So if flux increases, then induced current try to decrease flux. If flux decreases, then induced current will try to increase flux. Through this change in flux, through this opposition, basically your energy is conserved. Induced current oppose change in flux. If flux is increasing, then current will try to decrease flux. If flux is decreasing, then current will try to increase flux. Through this opposition, energy is conserved. We will see through several examples of energy is conserved in these type of cases. So this Lenz's law is in accordance with law of conservation of energy. With law of conservation of energy. So to solve problem of Lenz's law, you don't need any formula. You just need right-hand thumb rule. E is minus of d phi over dt. This negative sign is Lenz's law. Through examples, we will see how this opposition actually leads to conservation of energy. But to start Lenz's law, I need all laws that we have discussed in magnetics. All types of right-hand thumb rule that we have discussed in magnetics, I will use it here. So this topic, Lenz's law, directly connect to the right-hand thumb rule of magnetics. All type of right-hand thumb rule. So let's recall some rules. In magnetics, we did a portion known as magnetic dipole moment of a current carrying coil. We have discussed if the current in the coil is clockwise, then this phase will behave like, you remember if you have a coil and the current through the coil is clockwise, then can you guess how this phase will behave at the south pole or the north pole? If the current is clockwise, how this phase will behave, which behaves like the south pole or the north pole? If the current is clockwise, then it will behave like south pole. If the current is anti-clockwise, then this will behave like north pole. We did few more things, that if you have a coil and if current is flowing through the coil, can you guess the direction of magnetic field? This we did in chapter number 4 in magnetics. If you have a coil and a current is flowing clockwise, what's the direction of magnetic field? Inwards, right? We have studied right-hand thumb rule. Just curl your finger along the sense of current. This thumb will give the direction of magnetic field, right? So your magnetic field is inwards here. In calculating direction of induced EMF, the steps would be reversed. You would be having the direction of magnetic field. Using right-hand thumb rule, you can predict the direction of current. So right-hand thumb rule for direction of induced current. For the direction of induced current, right-hand thumb rule says just place your thumb in the direction of magnetic field. Place thumb in direction of magnetic field. Curvature of finger will give current. So the curvature of finger will give the direction of current. If you apply this rule here, take your thumb, place this thumb in inverse direction, your curvature will give the direction of current. In questions of induced EMF, you usually have the direction of induced current. The direction of magnetic field. You have to predict the current. So just place your thumb along the magnetic field. This finger will give the direction of current. There is not a single formula to solve numericals of Lenz's law. For different type of questions, you need different type of approaches. So I'm dividing questions in types depending upon the type of approach that I'm using. The type 1 question will have a coil and a magnet. If magnet is stationary, that means no current is flowing through the coil. The magnet is moving towards the coil. Can you predict, will there be any induced current or not? This coil will have any induced current or not if the north pole of the magnet is moving towards the coil? Yes, it will have, because the flux will change. You have to predict what is the direction of current here. Is it clockwise or anti-clockwise? The question is, this is the coil, this is the magnet. Magnet is moving towards the coil. You have to predict the direction of current in this coil. So to predict the direction of current, just move this magnet towards the coil. When you move this north pole of the magnet towards the coil, then this coil will try to oppose. So first of all, in these type of questions, you have to decide what is the cause of change in flux. The cause of change in flux is approaching north pole. Approaching north pole. Next, the coil will try to oppose its cause. So to oppose this approaching north pole, coil will induce some north pole here. Because to repel north pole, you need north pole. North pole is approaching towards the coil. So opposition, the coil will try to repel north pole. To repel north pole, this coil needs a north pole. Right? This phase should be north. Then only it can repel the magnet. And for the north pole, the current will be anti-clockwise. So if you have an observer here, this observer will see that current is anti-clockwise. So that's, let's say, first question on this side. So in these type of questions where you have a coil plus a magnet, first identify the cause. The cause is approaching north pole. Then decide how will you oppose that cause. You will oppose that cause that's approaching north pole just by repelling it. To repel north pole, you need north pole. So this face of the coil will behave like the north pole. If it is north pole, then current will be anti-clockwise. Is it clear? This first question. Different type of questions have different approaches. There's not a single formula for Lenz's law. Yeah, if it's south pole, it will be clockwise. Let's do one more question. This is the coil, and let's say instead of north pole, south pole is approaching. Then it will try to oppose the south pole. To oppose south pole, it will repel south pole. To repel south pole, your current should be clockwise. So if you have an observer here, then the current will be clockwise for the south side. Okay, now solve this one. This is your coil. The magnet is moving away from the coil. Can you predict the direction of current in the coil? This is your observer. Can you predict the direction of current in the coil? This I means your observer here. Clockwise, anti-clockwise. Can you predict the direction of current? Okay. Good, Jumena. Very good, Fatma. Johanna? See, if the south pole, the cause is receding south pole. So opposition by attracting south pole, right? It's moving away from the coil. So to attract south pole, you need a south pole. Sorry, not south pole. You need a north pole. And the current would be anti-clockwise. Is it clear? Since south pole is moving away from the coil, this coil will try to attract the south pole. To attract the south pole, it should behave like a north pole. This is your magnet. This is north pole. This is south pole. It's going in this way. Can you predict the direction of current here? Clockwise, anti-clockwise. Yes, it will be good. Clockwise, right? Current will be clockwise. Because north pole is moving away from the coil, it will try to attract this north pole. To attract north pole, it needs south pole. Very good. There's no need to write the whole explanation, but please write explanation for the revision purpose. Write as much detail as you can for this type of question. Because there's not a single formula these type of questions. You need these type of approaches to analyze it. Okay, solve this question. You have two coils. Predict the direction of current in each coil. Predict the direction of current in coil 1 as well as coil 2. See, the north pole is moving away from the coil. So this will try to attract this north pole. To attract this north pole, you need south pole. South pole means your current will be clockwise. Here the south pole is approaching. It will try, this coil 2 will try to repel this south pole. To repel this south pole, this will behave as the south pole and this will be clockwise again. So in both the direction of current is clockwise. Both the coils' direction of current is clockwise. Next we have type 2 questions. So this is your magnetic field. I call this as given field. Okay, this is your given magnetic field, which is inverse. I'm taking this coil inside the magnetic field. Now, as this coil moves inside the magnetic field, this is coil number 1, then flux linked with the coil will increase. So I'm solving coil 1. Flux linked with coil increase. With coil increase. There's a different approach for these type of questions. You can't solve these type of questions using the approach of north pole and south pole. Induced current will try to decrease flux. Induced current will try to decrease this flux. So to decrease this flux, induced current will try to decrease the flux. So decrease this flux, this current will generate a magnetic field. Induced current will generate a magnetic field which is known as induced magnetic field BI in a direction opposite to that of given magnetic field. Opposite to that of given magnetic field. So this is it. So the coil is moving inside the magnetic field. Induced current will generate a magnetic field BI, known as induced magnetic field. The direction of this induced magnetic field is opposite to that of given magnetic field. So your induced magnetic field is outwards. The induced magnetic field is outwards. It's outwards. So if your BI is outwards, you can predict the direction of current. Just take right hand thumb rule. Take your thumb, put it outwards. The fingers are curling in anti-clockwise direction. Just place your thumb in the direction of induced magnetic field. Your induced magnetic field is outwards, your current is anti-clockwise. So induced current is anti-clockwise. We can take one more example. Like say if this coil is going outwards. Example 2. This is coil 2. If coil is moving outwards, can you tell me how the flux is changing? It's increasing or decreasing? Yes. Flux is decreasing. Flux is decreasing. What induced current will try? It will try to decrease or it will try to increase? it will try to increase. So to increase flux, this induced current just have this induced magnetic field. So in what direction this induced magnetic field should be? It should be in opposite to that of given magnetic field or same, in the same direction? Same, not opposite. Fatma, if it is opposite, then they will subtract out. If magnetic fields get subtract out, then flux will decrease. You want to increase flux. So induced magnetic field will be in a direction same to that of given magnetic field, right? Fatma, you don't want to decrease flux, you want to increase flux. So to increase flux, your magnetic field should increase. Your original magnetic field is inverse. If your induced magnetic field is also inverse, then only the net field will increase, right? So BI is inverse. Apply right hand thumb rule and tell me the direction of induced current. Put your thumb in inverse. Put your thumb inverse. Your finger is clockwise. Okay, just tell me one more question. So if this is the coil, this is moving within the magnetic field. It's moving within magnetic field. Neither is going inwards nor outwards. That means your flux is constant in 3. This is coil number 3. It's moving within the magnetic field only. It's neither going inside the magnetic field nor it's coming outside the magnetic field. It's moving within the magnetic field. The flux is neither increasing nor decreasing. Flux is constant. If your flux is constant, then how much is induced EMF? Yes. I induce would be 0. This is so that's the thing. So if your coil is within the magnetic field only, it's not moving inwards or out of the magnetic field, then induced current is 0.